about modular inverters or even associators. He just talks about the motivic structure on SL2. So he says SL2Z avec sa structure arithmétique soit une véritable machine à construire des représentations motiviques. So SL2Z is a machine for constructing motivic representations of the absolute Galois group. And so this talk is in that sort of theme. And the first thing I want to do is talk about associators first, just to set a context for what I'm about to do. So, whoops, sorry, I get my page. Yeah. So Grothendieck in his Esquisse program suggested that you study the absolute Galois group via its actions on the profinite fundamental group of the projective line minus 3 points. And there was a missing ingredient that was provided by Bailey in 1980 that showed this action is actually faithful. So then a question becomes, how do you characterize the image of the absolute Galois group in the outer order morphisms of the geometric fundamental group of P1 minus 0, 1, and infinity? So that's a free profinite group on two generators. And so Ihara made the following observation. I believe this is due to Ihara, but it's a very basic observation. If you look, for example, at just, so I'm going to take two tangent vectors, this tangent vector here, this tangent vector here, and I'm going to get, so think of these as base points, tangential base points for P1 minus 0, 1, and infinity. And then I've got several paths here. I've got, so you could think of the groupoid with objects, these two tangent vectors, and morphisms, just paths between them. So there's this path here. There's this path here. Whoops. It's basically the loop around 1, and I'll call that gamma of 1. And there's this loop here, which I'll call gamma of 0. And this path here is, well, at least Francis calls it, I'm actually going to call it delta. And maybe Deline, and certainly Francis calls it le droit chemin. This straight line path here. And sometimes I'll denote it by DCH. All right, so if you haven't, so the claim is to understand the Galois action on the fundamental group of P1 minus 0 and infinity, you really only need to know how it acts on this path here. So let me expand on that a little. So if I take an element of the Galois group here, so it acts on the little loop about A, where A is 0 or 1, by raising it to the chi of sigma power. So what's chi of sigma? Chi is the cyclotomic character of the absolute Galois group. It tells you how sigma acts on a root of unity. It just raises it to this power. And so another way to think of this is if the logarithm makes sense, which it will later on, this is saying that sigma of log of gamma is pi of sigma times log of gamma A. So I'll put that in quotation marks because that doesn't make sense in the profinite case. But this tells you that the logarithm of gamma A spans a copy of z of 1 or z hat of 1. Right, so that's just all right. So that, for example, if you replace Q by the field you obtain by adding all roots of unity, the Galois group will act trivially on these two loops. And so everything else is determined, the entire Galois action is determined by the Galois action on delta. So All right. So DCH is the prototypical associator. You can get other associators out of this by, for example, think of just the topological path here. It gives you a profinite path from this tangent vector to that one. I guess I should have labeled these tangent vectors. Just the obvious notation here. This tangent vector will be called 0, 1 because it's at 0 points towards 1, and this one's called 1, 0 because it's anchored at 1 and it points toward, points towards 0. Right, so DCH can be thought of as a profinite path from 0, 1 to 1, 0, and it can also be thought of by the KZ connection from as a pro-unipotent. It gives you a pro-unipotent path from 0, 1 to 1, 0. So I'll discuss both of these points of view. In somewhat sense, the Galois picture gives better motivation. So, and so this part here you might think is so I couldn't see that whether Grothendieck discussed associators. I don't think so. But then you have Ihara, I think, who made the observation about who studied how the Galois group acts on the fundamental group of P1 minus 0, 1 and infinity. Deline and Drinfeld, and then on the other side, the periods of this path. This determines the mixed Hodge structure on the unipotent fundamental group of P1 minus 0, 1 and infinity. With, say, I'm going to take base point, say 1, 0. I like my base points to be anchored at the identity. Think of this as the multiplicative group with the identity removed. And this is KZ equation, Drinfeld, Deline. All right, so so let's discuss a little bit the relations here that on a that satisfied by, sorry for all that, relations satisfied by associators. They basically all come from topology. So any relations you have on associators or on DCH will constrain the Galois action. So this leads to, I guess, Grothendieck-Teichmüller theory, and they constrain the periods on the mixed Hodge structure of the unipotent fundamental group of the punctured projective line. So to talk about this some more, we'll just recall that MGN is the Deline-Mumford moduli space or stack or orbifold of n-pointed smooth projective curves of genus G with, and you require that the 2G minus 2 plus n is positive. This just simply means that the Euler characteristic of a curve of genus G with n points removed is negative, so that the surface is hyperbolic. And so its Deline-Mumford compactification will be MGN bar, and we won't need much of this. I just put it up there because it's easier to say it in general. So here, it's important to note the cross ratio here gives you a map to P1 minus 0, 1 and infinity. And this map is an isomorphism. Both of these are actual varieties. They're not stacks, and this is an isomorphism of varieties. So it's useful to think of the projective line as M04. So let's take a closer look at M04. So there's various structures here. So the first thing is, let's just point out here's M04. the real points, closure is the equator. So that the equator is the circle determined by 0, 1, and infinity. You've also got an action of sigma 3 on this. It's the permutation group. You should just think of it as automorphisms. I'll do that throughout the talk. It's just the automorphisms of the finite set 0, 1, and infinity. M0 for bar is just P1. So the complex points, this is P1C, and this is P1R. And I'm going to let, so I'm going to call this path, I'll call that delta AB, because I don't want to write DCH AB all the time. So it's a path from A to B, where A and B is distinct elements of 0, 1, and infinity. And it's going from the tangent vector AB to the tangent vector BA, right? And now, so for example, we'll have these two tangent vectors here. The sigma 3 action spreads it around, so you get 6 canonical tangent vectors. So it's natural to look at the fundamental groupoid of the sphere with these 6 tangent vectors. And we also have, let me see if I want to put them in yet. Yeah, and we also have the paths, these paths here. So we have this path, that's no good. We have this path, which goes from this tangent vector to that counterclockwise. We have the other one here, this one here, and I'm going to call this gamma 1 plus. So, and this one I'll call gamma 1 minus, and I have similar things here and at infinity. So there's 6 of those loops. So maybe I'll just draw a little picture. If this is A here, just to make it abundantly clear, this loop here will be called gamma A plus, and this loop here will be called gamma A minus, and gamma A plus, gamma A minus is just gamma A. Right? So these, so you can look at the fundamental group of P1 minus 0, 1, and infinity with these 6 objects, the 6 red tangent vectors, and you have the 3 or 6, depending on how you count, prototypical associators or straight line paths, and then you have six of these sort of semicircular paths. And how do we get our relations? Well, the first relation just says that if you take a straight line path and you reverse the direction, you get the other straight line path. There's nothing surprising there. The next one is simply that if I go along here, say around gamma minus, around here, around gamma minus, around here, around gamma minus, that loop is null homotopic because it bounds the southern hemisphere. So that's the 6-term relation. So we get gamma 0 minus, gamma 0, 1, gamma 1 minus, gamma 1 infinity, gamma infinity minus, whoops, I didn't mean it. I mean delta. Yeah. Let me do this again. It's not my usual notation. Gamma 0 minus, delta 0, 1. Gamma 1 minus, delta 1 infinity, gamma infinity minus, delta infinity 0 equals 1. That's the 6-term relation. And then the final relation is another relation is the 5-term relation. And this comes from all the inclusions of M04 into M05 bar. There's, I think, 12 of these. And in particular, as boundary strata, open boundary strata. And I mention this way because this is a one-dimensional moduli space. This is a two-dimensional moduli space. And in the elliptic case, there's going to be one-dimensional moduli space, M11, the modular curve. And there's one two-dimensional moduli space, which is the universal elliptic curve. We're going to get relations in that case from the same sort of consideration. Anyway, if you look at M05R, this 12, this guy here is a union of 5 pentagons. So the boundary of this is not actually in M05. This is in M05 bar. But you can take little tangent vectors at each vertex, and you can look at, say, this path here. And that path is null homotopic because it bounds this disk in the real points of M05. And you can compute that monodromy just by going along these 5 paths here. This is just standard yoga with tangential base points. And if you take the product of these 5 guys, you get something trivial, and that leads you to the 5-term relation. And I will add one more here because it's sort of relevant to this conference, is that there is, I'll just say it very briefly, I've been meaning to try to study it, but there is the Turayev co-bracket, and you can take the reduced Turayev co-bracket, which is going, and I'll say delta AB, and this is going to be equal to 0. So I don't want to explain that further, but these are all topological relations, and so is this here. The Turayev co-bracket it's actually this. So it takes a path from, say, one point to another on where the 2 points are on the boundary of the surface into something that's in the tensor product of paths and free loops in the space. And so an obvious thing about DCH is that its co-bracket is 0 because it has no self-intersections. And so years ago, I mentioned this to Francis Brown, and he pointed out that that surely, or maybe, implies the double shuffle relations. It encodes the double shuffle relations. So that hasn't been worked out. So, all right. So, and if so, that would give a nice simple explanation of double shuffle. So let's turn to the elliptic case now. So as I mentioned before, the basic object here is the other one-dimensional moduli space. There's only 2 of them, M04, which is the story of the associator, and M11, which is the modular curve, which is truly an orbifold or a stack. So the moduli space of one-pointed genus 1 curves, that's the same as the moduli space of elliptic curves. Analytically, as an analytic orbifold, it's the quotient of the upper half plane by the usual action of SL2Z. And to work on this just means you work SL2Z equivariantly on the upper half plane. Or algebraically, if you're that way inclined, you can take, it's defined over Z, but it's a stack over Q. It's just, you just take the affine Q space and you remove the divisor D. So D is going to be delta inverse of 0, where delta is equal to u cubed minus 27v squared is the discriminant of the cubic y squared equals 4x cubed minus ux minus v, right? So this is all very standard. So the point uv in A2 corresponds to this elliptic curve, but you get the same elliptic curve many ways here for different choices of u and v, but you get the same elliptic curve if they lie in the same GM orbit, where t times uv is equal to t to the fourth u t to the sixth v, right? So that's the GM action. So note that -1 acts trivially here, as it does in the case up here, where minus the identity SL2Z acts trivially. So that's a bit of that complicates matters slightly, and I'm largely going to ignore it. So the orbifold fundamental group of the modular curve is isomorphic to SL2Z. Of course, this isomorphism will depend on the choice of base point, and I'll be more precise about the particular base point we want later. And the Ital fundamental group is SL2Z profinitely completed. Okay? So when we talk about the Galois, and this thing admits a Galois action, it's not hard to see. You first of all consider the Galois action on the profinite fundamental group of this and show that it descends here. You can't use the usual construction because M11 doesn't have a function field. All right, so let's discuss SL2Z a little bit. So it's standard, and I have to use these non-standard letters. Normally people would use S and U for these guys here, but those letters in this story have other letters. So SL2Z has a presentation. It's generated by an element of order 4 and an element of order 6. And the square of the element of order 4 is, so the element of order 4 is this guy here, is minus the identity, and the cube of the element of order 6, which is this guy here, is also minus the identity. So that's the presentation. And this guy here, the upper triangular unipotent matrix here, I'll call gamma, also known as T. And so we can also rewrite the presentation as being generated by the element of order 4, rho, and gamma. And you'll see why we did that in a minute. And the relation becomes this guy here, that rho is equal to gamma, rho, gamma, rho, gamma. Okay, so this guy, so let me draw the picture. So let me give you a geometric interpretation. So to do this, we look at the Q-disk. So if you take the upper half plane, so the parameter in the upper half plane, I will call tau. And if you divide by the action of this group, so this group here, 1n01, just by the usual rule, just takes tau into tau plus n. Okay? So it's just translation. And so when you divide by this group, there's a natural holomorphic coordinate q, which is e to the 2 pi I tau. And so you have a map from this guy into this, because this is a subgroup of that. So you get a map from D star into here. And I'm going to, the generator of pi 1 of this punctured disk is our matrix gamma, this guy here, it's this guy here. So it generates a copy of Z. And so, yeah, and again, the standard yoga of figuring out how the Galois group acts on these fundamental groups tells you that sigma of gamma is just as before, it's gamma raised to the chi of sigma. Or if you like, sigma of log of gamma is equal to chi of sigma times log of gamma. Right? So this will make sense once we get into the pro-algebraic setting. which is telling you that log of sigma really spans a copy of Z of 1. So we understand the action on this guy. So here's a schematic picture of the modular curve. First of all, it's a quotient of the upper half plane by SL2Z. The element rho swaps 0 and infinity. So rho takes tau to minus 1 over tau. So the loop rho is this guy here. That path there descends. Oh, I guess I'll put an orientation on it. It descends to the element rho in the fundamental group. And so if you take the quotient here, you get a weird thing because you've got a couple of coding points, which I'll ignore. There's one at I, and there's one at a cubed root of unity. And so here is a small q-disk. The q-disk doesn't inject, but it does. If you restrict to a subdisk of this q-disk, it will inject into M11. And so here is a small q-disk, and the loop gamma is the loop around the cusp. So here it is here. So this is going to be gamma. And I'm going to take it to be based at ddq, the tangent vector of the disk. Yeah, I should have done this over on this slide. So here is the base point I'm going to use is here's the q disk, here's the origin, and here's ddq. And ddq actually points out along. So the image of the imaginary axis in the q disk is just the positive real axis. So this guy points in the direction of the path, this path here. So this path here turns out to be a loop that goes from, this is a path, this is ddq here, and this is ddq up here. And so this is a loop based at ddq. And here's our ddq right here, our tangent vector. And our path, so we understand the Galois action here. It's basically trivial. If you go up to, if you join all the roots of unity to Q, the Galois group will act trivially on this guy. So again, the entire Galois action on SL2Z is determined by this guy here. So you should think of this path as going out here, doing something funny at I, and coming back. You know, you can do this, you can go down here to I and back up. And so the point is here, the fundamental group of some sort of neighborhood of I is actually Z mod 4. It's the automorphism group of the corresponding elliptic curve. All right, so that's the picture. So it's completely analogous. The Galois action here is just given by the cyclotomic character. So the rest of the Galois action on SL2Z is determined by the Galois action on rho, the element of order 4. Excuse me. So as before, there are two kinds of relations. There's ones that come from the topology of M11. So these would be the analog of the 6-term relation. In fact, they're very closely related to this one's very closely related to the 6-term relation. So you've got that the 4th power of rho is 1, and you've got this relation. And the other kind of relation you get is from the inclusion of M11, so the modular curve, into M12, into M12 bar as an open stratum. And I will explain this in a second, but so yeah, this goes in as an open stratum. And here there's only one way. This guy, as I'll explain in a minute, has only 2 boundary strata, unlike M05, which has lots of them. And let me just explain, yeah, there's 2 boundary strata. One's a copy of M11, and the other one is a copy of M04. So what is M12 bar? It's the set of all 2-pointed genus 1 curve. So you can think of it as an elliptic curve with 1 additional point, and that additional point can't be the identity. So it's the modular. So yeah. So what we're going to do here, it's really, there's a universal elliptic curve over M11. You can complete it to a curve over M11 bar, and this is M12 bar. So a point down here would be E, 0, and a point here would be the fiber over it is E, here is 0, and you have to choose another point on it, X. Right? So that's what M12 is. It's the universal elliptic curve. And inside it, what is M1? What is M12? It's just equal to, you take E, you restrict it to M11, so you remove the fiber over the cusp here, the point Q equals 0, and then you remove the identity. You remove 0 because X cannot be 0. And this will map down to M11. So I'll redraw all this in just 1 second. So M12 bar is the universal elliptic, stable elliptic curve, and M12 is the restriction of that to M11. So it's the universal smooth elliptic curve with its identity section removed. And so now here is the picture here. So here's M11 bar. M11 is obtained by removing Q equals 0. So the Q disk is here. We have our tangent vector here. I'm going to put in DDQ. And so upstairs here, here's the universal elliptic curve over M11 bar. The fiber over 0 is the nodal cubic. Here it is here. The fiber over, say, some other point will be a smooth cubic. So the fiber there would look like this. This here is the identity section, or I don't like to call it 0 because on this fiber it will be 1. But if you're thinking of the identity of your elliptic curve as being 0, then this is 0 on that elliptic curve. It's the identity. And so our base point is DDQ. What's the fiber over? It's like a first order thickening of the nodal cubic. And it's actually a smooth elliptic curve over the dual numbers. So this is going to be our fiber, and the mixed Hodge structure associated with it, or any mixed Hodge structure, will be a limit mixed Hodge structure. And there are similar ways to define limit Galois representations. And now another important thing we have here is that so M12, you remove the nodal cubic. By the way, the nodal cubic here, you should think of as it's P1 with 0 and infinity identified. So that's this guy here, and the identity here is at 1. So if I remove the identity section, and if I remove the double point, I get P1 minus 0, 1, and infinity. And that I can actually push out to first order onto my smooth elliptic curve. So this is going to be one way that associators are related to inverters. Inverters are going to be in this direction. It's rho. Rho is going to be the prototypical inverter, and associators are things if you like, in this fiber. But we want SL2Z or SL2Z to act on the fundamental group of the fiber. And it doesn't. You have to thicken the group up slightly. So what we do is we look at the punctured normal bundle. So we take a little tubular neighborhood, if you like, of the identity section. There it is. And we remove the identity section. So this guy here, so the normal bundle with the identity section removed is going to be called, I'll call it M1 vector 1. That's this guy here. So M1 vector 1 is equal to the moduli space of elliptic curves, say smooth elliptic curves, and V, where V is in the tangent space and 0 of E, and V is not equal to 0. And that's basically, this is telling you how to deform the identity to first order. You just follow this tangent vector. So yeah, I don't have a slide for this, but let me just say a few things here. Two things are true here that I think this is on a later slide, but M1 vector mun is equal to A2 minus this divisor I defined earlier. This was U cubed minus 27 V squared equals 0. And its fundamental group, so pi 1 of M1 vector 1 base point is isomorphic to the braid group on 3 strings, and SL2Z, as I'll explain later, as you would expect. So this is going to be a C star bundle over M11. Right, so this tubular neighborhood here is a C star bundle over this, so the kernel should be Z, and so this is going to be, it's B3 modulo the square of a full twist. And so what we're going to do, we're going to have to lift rho up to this tubular neighborhood, and then pi 1 of this B3 is going to act by monodromy on the fundamental group of excuse me, the first order smoothing of the nodal cubic. All right, so let's look at this first order smoothing. We want to, it's fine and dandy to draw a picture here of this first order smoothing, but how do we actually work with it topologically? So if Q is in the Q disk, the fiber of the universal elliptic curve, so the corresponding elliptic curve over Q equals not equal to 0, and we're going to take the absolute value of Q less than 1, is obtained from an annulus. So remember that Q is equal to e to the 2 pi I tau. So this is just the story that descends from the usual way of writing an elliptic curve as C mod lattice. You can write it as C star mod all the powers of Q. So what this does is, if you take, a good way to do this is to look at absolute value of W. So this is in the W plane, equals 1 over the square root of Q, the size of Q. And this guy here is absolute value of W equals the square root of. And you identify a point on the outer circle W with Q times W, which will lie on the inner circle. And if Q is real and positive, these guys will line up. Otherwise, there'll be some sort of twist here when you identify the outer circle with the inner circle. So EQ is just this annulus with this identification. So what's the fiber of the universal elliptic curve over DDQ? So we take Q to be real and we let it go to 0. And so what happens here is that the outer circle gets bigger and the inner circle gets smaller, and these annuli converge to the real-oriented blow-up of P1. So as this happens here, this annulus converges to the blow-up, the real-oriented blow-up at 0 and infinity of P1. So think of that as you just take P1 and you've got 0 and infinity on it, and you replace these 2 points by little circles. And then what you're doing is you're still doing the same identification, and this leads you to the following picture. You're going to just take, again, it's this annulus where you join the outer to the inner, and you can redraw it like this. And so 1 will be over here. This will be the circle of oriented directions at 0. This is the circle of oriented directions at infinity. And now, how are you going to identify them? Well, on P1, there is a path from 0 to infinity, and you want to do it so that path closes up. And that's it. So this is going to be, this is our, and everything here except the boundary circle is really a copy of C or the affine line. And this is going to correspond to 0. Sorry, it's going to correspond to, sorry, it's a copy of C star or GM. So this is what happens to the real axis in P1. So this here is what I mean by E, D, DQ. And if I went out in a different direction, I would have to rotate these circles before making the identification. All right, so now what about its fundamental group? Well, if I take this first order smoothing of the nodal cubic and remove the identity, its fundamental group will be a free group on 2 generators. And what are the 2 generators? You can make it generated by this loop here and the blue loop. So you've got to identify the outer circle with the inner circle. And I'm going to create some sort of formal path here I'll call epsilon. It's completely inert. It has no Hodge theory and no, the Galois action on it is trivial, but it's convenient to put it there because it tells you how to get from this point on the inner circle to this point on the outer circle. And if I did this right, you get the relation, you choose the paths carefully such that alpha inverse beta inverse is equal to gamma 1, which as you recall is the circle around 1. Here, excuse me, here's 0. This is like an infinitesimal circle around 0. Here's 1. That's an infinitesimal circle about 1. And this is gamma infinity here. Right? So this is an infinitesimal circle about infinity. And this path epsilon has to satisfy the following sort of relation. It says that if you go around here and do epsilon, that's the same as doing epsilon and going around here. And so we have the cylinder relation which says that gamma 0 epsilon gamma infinity is equal to epsilon. Right, so I write that down because I'm now going to write down the formulas for alpha and beta. So alpha, the way I did it is delta 1 infinity. So I go out here. I'm going to go around infinity the wrong way. So then it's delta infinity inverse, gamma infinity inverse. Then I'm going to come back in here. So it's going to be delta infinity 1. So that's alpha. And beta, so you can see it's written down in terms of associators or prototypical associators. Beta is gamma 1 in minus. So you have to go around here. Then I'm going to go from 1 to 0. So it's delta 1, 0. Then I'm going to do epsilon to get out here. So that's epsilon is really the path, this path here. And then delta infinity 1. Come back to here. And all of these are based at this, the base point is 1 infinity. Right, so you should think of P1 minus 0, 1 and infinity sits inside this curve. This guy here, this contains right, so it contains P1 minus 0, 1 and infinity. So when I take the identity out, this contains P1 minus 0 and infinity. And this makes sense from the point of view of both Hodge theory and Galois actions. Right? So, so you should think of this description of the fundamental group as being in terms of things that are already familiar from the theory of associators. Everything here is a prototypical associator or one of these sort of trivial paths that go infinitesimally close to going halfway around 0, 1, or infinity. All right, so I've already talked about M1 vector 1. Yeah, so I've already mentioned M1. So the fundamental group of this guy is going to act on the fundamental group of this guy, and that's going to relate inverters to associators. It's going to give relations. And so I already mentioned the fundamental group of this guy of M1 vector 1 is the braid group on 3 strings. And this has a presentation, which should be familiar. It's just a braid presentation. It's generated by, I guess I didn't write this properly. It's generated by 2 guys, TA and TB, subject to this relation. And what are TA and TB? These are Dane twists. So these guys here are going to be Dane twists on two positive Dane twists. On which 2 curves, both of these guys are Dane twists, and A will be this curve, and B will be the real axis, this part of the real axis. So these are not based loops, but these are the free homotopy classes of alpha and beta that I defined before. And what I have to do is define lifts of my prototypical inverter and gamma, the loop around the cusp, to B3. So B3 maps to SL2Z. And TA, it's easy to check, maps to 1, 1, 0, 1, which was equal to gamma. So this TA naturally lifts gamma, and TB will go to 1, minus 1, 0, 1. And so you just play around a little bit to find a natural lift. So as I pointed out before, I'm going to lift gamma to gamma tilde, which is TA, and I'll lift rho to this guy here. And if you do that, you'll see that rho tilde, when you map to SL2Z, it goes to rho. And the basic proposition is how does the braid group act on the fundamental group of this first order smoothing of the nodal cubic? It acts in a very simple way. It takes alpha to alpha, beta to alpha beta inverse. Beta goes to beta alpha, and TB takes beta to fixes beta. Right. So this is easy to work out, just basic topology. And then from this, you deduce from this formula that rho tilde takes alpha to this conjugate of beta and beta to alpha inverse. And this is, if you check what this does on homology, it does exactly what rho does on homology. It takes A, the class of A to B, and takes the class of B to minus A. So this is telling you, if you write it all out, it's telling you relations between the prototypical inverter and associators. So it's symmetries you don't see just without looking at the elliptic story. And these formulas are all Galois equivariant. So they're, again, constraining the Galois action. So, all right, so now this gets to the hairier part of the talk. All right, to get mixed Hodge structures or L-adic linear Galois representations, you have to replace SL2Z by a vector space. And the natural way to do it is to replace it by an affine group scheme, or if you like, a pro-algebraic group. So I'm going to describe various G that we could use. So this G will be this, its coordinate ring will be some commutative Hopf algebra that won't be finitely generated in general. And the de Rham theorem will tell us that this guy here consists of iterated integrals. And in the modular case, we're going to get iterated integrals of modular forms, and the ones we get will depend on the particular completion we choose. So I've written various G. And I'm going to write down a whole zoo of completions. And the idea is not to intimidate you, it's to say that there's a choice. And some of these I've been led to in trying to understand the action of the Hecke algebra on certain iterated integrals. So the very efficient way to construct these guys is through Tannakian machinery. I'm not going to do any construction because it's just the people I think that already understand this, they already know how it goes. And excuse me, need water. And for other people, I think it's just confusing at this point. So it's better to see where you go with it. So I'm going to jump right in. So the general shape of one of these groups is that it's an extension of this is going to be a pro. So pro just means inverse limit. And reductive, think of groups like SLN. So it's a pro-reductive group. This guy's pro-algebraic. It just means it's an inverse limit of affine varieties that happen to be groups. And this guy here is pro-unipotent. So you're already familiar with pro-unipotent because, so it's an inverse limit of unipotent groups because that's what occurs in the KZ story. And so it's the, if you like, it's the inverse limit of extensions 1, U alpha, G alpha, R alpha into 1, where this guy is This guy here is reductive. This guy is an affine algebraic group, and this guy is unipotent. So, and you can actually even make this guy pro-unipotent. And in our case, well, U via the logarithm and exponential corresponds to its Lie algebra. And the exponential map here is an isomorphism. And in our case, U is free. It's always free. This is because SL2Z has cohomological dimension 1. So in all of our completions, the unipotent radical is free. That means its Lie algebra is an inverse limit of free pro-nilpotent Lie algebras. Actually, when do you want me to finish here? I think I started about 10 after. So, so for each completion, there's a homomorphism from SL to Z into this group. And the image is Zariski dense. No matter how humongous this guy appears to be, it is the image is Zariski dense. And in each case, there is an associated inverter. What will the inverter be? C, maybe I should write C of G, would be by definition just theta of rho. That's what the inverter is. And this would be the analog of the KZ associator. And now, how can this guy be written? So in some of these cases, I admit it's hard to write this down, but but you can, because you can always work in some finite dimensional quotient of this huge G. But how does this work? If you write G, you can always write it as a semi-direct product of the reductive quotient by the pro-unipotent kernel. So you have to choose this splitting, and then C is going to be an element of U crossed with R of, say, whatever field you're using. I'll just put R of C here, for example. And the element you get in, so it's going to, and this part here will be some sort of power series whose coefficients are iterated integrals evaluated on this path from 0 to infinity. So this is exactly like the classical KZ associator, whose coefficients are multi-zetas. And what you get here is some incarnation of the matrix 0, -1, 1, 0, just the image of this guy in this reductive group. All right, so what does this zoo look like? Here's zoo. So there's G huge up here and G big down here, and even G big is very big. And you've got Gn here, and maybe I should put G1. So I've written quite a few papers about G1, so you can see these guys are already a lot bigger. And let me say very briefly what and these guys here are interesting sort of new things. Well, they're kind of new, they're not. Yeah. So I want to shade the back here. These guys here are sort of all of these are virtually unipotent, and these guys here all come from modular forms. And let me try to, I'll leave this here for a second. What's gamma here? Gamma here is a normal subgroup of SL2Z of finite index. And Gn is going to be G of gamma n, where gamma n is the subgroup of SL2Z consisting of matrices congruent to the identity mod n. So this is really a special case of these guys. And a similar thing holds on this side here. All right, so so the first statement is that this guy is just the inverse limit of these guys. This guy is the inverse limit of these guys. And so similarly with this face. So that's what this slide says. It just says G huge is an inverse limit of these guys over all finite index subgroups of SL2Z, and G big is just an inverse limit over congruent subgroups. So this is the congruence completion. Okay. And, you know, in another project, I've been studying Hecker operators, and you're forced to go into something like this to study Hecker actions on iterated integrals. All right, so to tell you about these completions, it makes sense to tell you what the reductive quotients are and what the dual of the abelianization of the Lie algebra is. A free Lie algebra, a free pro-nilpotent Lie algebra is determined by its H upper one. So up to isomorphism, what I'm telling you here will determine each of these up to isomorphism. So what's G gamma? So I told you that gamma is a finite index normal subgroup. So this is of SL2Z. So this is just the quotient. So it's a finite group. This is the inverse limit of these. So the reductive, and this is just usual SL2 over Q. And every finite group is considered as an affine group scheme in the usual way. You just take the dual of the group algebra. It's a commutative Hopf algebra, and that's it. So if you take the inverse limit, you get the profinite completion of SL2Z here, which is huge. If I take Gn, it's the reductive quotient. It's just a special case of this. The quotient of SL2Z by principal congruent subgroup is just SL2Z mod n. When I take the limit, I get this guy instead of this guy. So I just get SL2Z of Z hat. So this is my favorite guy at the moment. And I'm not going to worry too much. Yeah, P gamma, the quotient will just be G gamma. We're not going to use the algebraic SL2. And Pn, the reductive quotient will be just SL2Z mod n. So this guy is an extension of SL2Z mod n by a pro-unipotent group. And maybe I should tell you what the H1s are. Let me just pick the favorite ones. So this one here is going to be the direct limit of m greater than or equal to 0, H1, Yn. So Yn so Sm means the mth symmetric power of the defining representation of SL2. Yn is the quotient of the upper half plane by the principal. So Yn is equal to, this is absolutely standard, the quotient of the upper half plane by gamma n. And this guy is just going to be the inverse limit of these guys. So this is just going to be the inverse limit over n of these guys here. And this guy here, the H1, so this guy here gives you modular forms of all weights. When you take the inverse limit, you get modular forms of all weights and all levels. And I should point out that SL2Z mod n acts on this. So this H1 has got to be a representation of this group here, and SL2 acts on that. And here you get the same, but you only get modular forms of weight 2. So you get H1 Yn with rational coefficients, box times. Yeah, that's it. And SL2Z mod n acts on this. So this is just modular forms of weight 2. This is just weight 2. Okay, so if let me very briefly say this here. So there is if G is any one of these groups, the coordinate ring has a natural mixed type structure. For each prime number, the natural map of SL2Z into here extends to a map from the profinite completion of SL2Z into here. There is a Galois action on this guy when you tensor with QL, and there's also a Galois action on this, and this homomorphism will be Galois equivariant. So this is a Galois compatible algebraic completion of the group that also carries a mixed type structure. And so, yeah.
Right. You have just 1 minute to finish.
Okay. Well, maybe let's see what I could say. I'll stop here. I mean, basically, how you work with these, it looks hopeless, but you work with a specific quotient. And I'll mention one that's kind of relevant. I was going to do 2 or 3 examples, but if I take P2, you need to understand what this guy is. This is the modular curve of level 2, and it's very closely related to P1 minus 0, 1, and infinity. But I want to emphasize that this is a completely different manifestation of P1 minus 0, 1, and infinity, which has all sorts of modular forms hanging off on it. And I was going to do this and explain why one of the modular relations gives you the 6-term relation, although I suspect that's already sort of known. But what's different here is that there are modular forms of all weights occurring here. And yeah, so let me stop here. I don't want to hold up your dinner.
So questions? So if not, let us thank the speaker again.